Hey there, in this video I want to talk about the FTCS method. FTCS stands for Forward Time Centered Space. And this method is a combination of the relaxation method and the forward Euler method. So at this point you might be thinking, why can't we just use relaxation method to do everything? And there's a couple issues there. One though is fundamental. If one of our independent variables is time, and we tried to do relaxation method, we would have to have boundary conditions. That means we would have to know at t final, what does our system look like everywhere? Because that's a boundary condition. And so if we don't know that, if the entire problem is to figure out, given some starting conditions, how does my system evolve, then I cannot use the relaxation method. So that's what this method's for. We treat time differently than space because the general idea is we may know boundary conditions in space, like at the edges of a box, but we don't know the boundary conditions into the future. What is the system everywhere going to look like in the future? So here's our basic recipe. So step one is to take the spatial part, the x's and the y's, and we're going to treat it as a finite difference. And then the second part of this is to treat time as special, mostly dealing with what we already know. And we're going to do that with a ordinary differential equation type technique. In particular, with FTCS, we use the forward Euler method. It was the very first way we tried solving ordinary differential equations. Now, if you're wondering, why do we use this? Why don't we use a Runge-Kutta, for example? And the reason for this is twofold. One, Euler method works very cleanly with arrays. It's easy to write array equations that use Euler's method. And number two, we wouldn't actually gain any measurable accuracy with Runge-Kutta because the finite difference that we're doing up here is already kind of lousy, already has pretty poor error scaling. So doing a Runge-Kutta here doesn't really gain anything. In other words, we don't lose anything doing Euler's method, and it's easy to code. So that's why we couple this with Euler's method. Now, eventually we're going to talk about something called the Crank-Nicolson method, which deals with the fact that the forward Euler method is really terrible at conserving energy. And so that leads to systems that tend to explode. But for now, we're going to ignore that possible issue. Okay, so let's give this a concrete example. Let's do the diffusion equation, also called the heat equation. So temperature as a function of time, or at least its derivative, is equal to a diffusion coefficient times the second derivative of temperature with respect to position. So this is really like a Laplacian, but we'll do it as a one-dimensional problem. Okay, so let's go through the two steps in my recipe. So the first thing here is to take this dx dt and do a finite difference on it over here. So the left-hand side is going to become an ordinary differential equation because now this time here is the only term with the derivative in it. And on the right-hand side, we're still going to have capital D, and we're going to do the finite difference to change that second partial derivative into t at x plus, before we were using h's, but we want to use h with time because we're going to have to do that in just a moment. So we're going to use a's here for sort of like my spacing in space. So x plus a, and it's still a function of time. And then we're going to do t at x minus a, and then subtract 2 times t at x and t. Divide all of that by the spacing a squared. And so the idea now is that suppose t is represented as an array of values. Let's say there's capital N values in there. Then what this line here represents is n simultaneous ordinary differential equations. And n is probably a lot, like at least 100. So that's one of the reasons why we don't want to use something like Runge-Kutta. As amazing as it is, it's ultimately slower than Euler's method, and when you're multiplying that by a factor of 100, it can start to matter. So we have these n simultaneous equations, which we're basically going to represent just as a single array equation. Okay, so now to get the time dependence, what we're going to do here is note that we have written the derivative of temperature with respect to time in the form that works nicely with Euler's method. So there's this function here of temperature and time. That's this thing that we wrote over here with the finite difference. And this is true for every element in t. Okay, so what that's going to lead us to when we do the forward Euler method is finding the temperature at the next time step. So h here represents a time step. Is going to be equal to the old value of temperature plus the time step times that function f, where again f is this thing over here. So let's just plug it in and get our final result, and then we can try it out in the notebook. So the next value of the temperature is equal to the previous value of the temperature plus h times this function here. So this is going to give me an h capital D on a squared as a combined coefficient, and then I'm going to have t at x plus a, t at x minus a, and then temperature at minus 2, temperature at x and t. And so for the diffusion equation, this is what the FTCS method gives us. And like we talked about with finite differences, if you change your equation, you get a different final result. So it's not really worth drawing a box around this because it's specifically for the 1D diffusion equation. But this is the approach you would take to turn the partial differential equation ultimately into a set of equations that you're solving, represented as the elements of an array. So here we are back in the notebook, and I've copied down our expression for temperature after applying the FTCS method. And to make this a more concrete example, let's use a made-up diffusion coefficient. We'll do a wall thickness of 10 centimeters, one side at 0 degrees, the other side at 100 degrees, and the wall itself starting at a uniform 50 degrees, and then cooling on one side, warming up on the other side. And I think what I want for a final result is, since we're doing the time evolution of the temperature in this wall, I think it makes the most sense to do an animation. So we'll plot temperature as a function of space in a graph, and then we'll animate that graph for different values of time. And there's other ways we could visualize it as well, but I like my animations. All right, so starting point, as usual, is to just get these constants defined. So we'll do d, L, and the other ones here will be when we set up our initial conditions and boundary conditions. Also a good idea to set how long I want to run time for. That wasn't one of the statements in my problem, so I want time to be long enough that the temperature reaches an equilibrium. So there's a little bit of trial and error to how long is long enough. I happen to know that 100 is long enough in this case. Now we want to set up a spatial grid. That's going to be a grid for the x spaced by amount a. So that was set in the problem statement as ranging from 0 to L. And let's go with 101 numbers, or 101 points. That gives me a spacing of 100. So that when I calculate a, I'm going to take L and divide by 100. So notice how these numbers match up with each other. We're going to do the same kind of idea in time. So let's call that array time. You're wondering, why don't I call it t? It's because I want to use t later on in my program. So I want to do like for t in time. And so anyway, my time array is going to go from 0 to the t max that I set up here. We need a lot more time steps than we need space steps. So having played around with this a little bit offline, 10,001 works pretty well here. Actually, maybe we should write this a little bit more explicitly just so it's easier to see what the number is supposed to be. So 10,001. And this has to be an integer, otherwise I'd write 1e4 plus 1. Anyway, back over here, t is going to be t max divided by 10 to the 4. And this one can be a floating point number. Again, we want to make sure that these things are consistent. Weird stuff happens if your arrays don't actually match what you said H and A are, so watch out for that. Okay, so now we need initial conditions and boundary conditions. So capital T will be my temperature. And I want to start with everything equal to 50. So the easiest way to do that is to make an array of 1s and just multiply it by 50. These numbers here have to match. So it's a one-dimensional array. It has to have 101 things in it. It would be safer to make these things be variable. But, oh well, too late. Already typed up the numbers. Okay, so it's my initial... No, I spelled it right. Conditions. And then we have our boundary conditions. So the boundary conditions say that T0 is, that one was 0, and the last value in T, we'll make that one 100 to match our boundary conditions. Okay, now we can do the actual method itself. So this will be a for loop, so for t in time. Here's where we do Euler's method. This kind of looks like a relaxation method, but it's not, it's Euler's method. So there are some differences here. In the relaxation method, we would continue this for loop until hitting a tolerance. With Euler's method, we go until we run out of time, taking step size h. So that's why it's important that h be small enough that we kind of have to like converge as we go. All right, anyway, in here, we're going to do, basically we're going to take this line of math up here and put it into Python code. So we want to make sure we never change the boundary conditions. So we're going to slice just the middle of the array temperature. And then at each step, the T new is equal to T old plus some stuff. So we can just do this as a plus equals. We have H times the diffusion coefficient divided by little a squared. And then we take that and multiply it with neighbors to the temperature. So we're going to take T and 2 through the end plus T all the way up to the last 2. And then it was minus 2 times T itself, but we don't want to include the boundaries there. Okay, and so this will do the calculation and store in the array T what our final temperature is. Now, if I wanted to see the temperature step by step, I should keep track of what was in T. So I'm going to make a list here that stores values of temperature as we go. And at each step, I want to append into that list. Now, I guess you can argue about whether we should, oh, careful, this has to be a copy, whether we should append before or after calculating. Do we want the starting value or not? Now, this animation is going to play so quickly you won't visually tell the difference, but it is something to think about. Okay, so that's the code. Let's just run this cell because it should do the calculation and populate temperature, and then we'll see if we have any bugs or if it ran. Okay, looks like it ran. So now let's try animating it to see what actually happens. We calculated an awful lot of temperature values, about 10,000 of them, well 10,001 of them. And so I don't really want to make an animation with 10,000 frames. I'd like an animation with, let's say, 100 frames. So we're going to skip every 100th of them. Then we have our boilerplate animation code. So we create a figure. We make an empty plot. And we set it equal to a variable that I'm going to call line. I'm going to update line. Let's go with red, because that just sort of feels like a temperature color to me. We should set our limits, so 0 through capital L. Y limits here should be 0 through 100. I think we might actually get away without setting limits in this particular case, because we have those two corners fixed, the two boundary conditions. Still, it's always a good idea to explicitly set your limits if you're going to animate. In our animation function itself, what we want to do is set data. So line.set data, and what we're going to set it to is temperature at frame multiplied by skip. So we're not doing every single element, but every 100 elements. Oh, you know what? That's not quite. That's just the y values. So that's like our. That's our y values, and our x values are the array x defined up here in the previous cell. I should be setting x's and y's. Okay, that looks a little better. Okay, and then we're going to do our func animation stuff. I mean, this code never really changes. Func animation fig animate total number of frames is going to be equal to the length of the temperature array. Integer divide by skip. I mean, I could figure this out, but that's effort. Interval is, we'll start with 20. Anim to HTML5 video. Okay, so we, the magical incantations that make animations appear, right? And let's see if I spelled it all right. Okay, it's running. Shouldn't take too long with just 100. Oh no! Oh, to play. Oh no. Okay, try again. And nothing's changing. What did it either it converged super quickly, and I mean this makes sense for a final value. We have 0 at one corner, 100 at the other, and it's just a nice straight line connecting them, sure. But I expected to see it change shape. So I did my t.copy. Like, this is what it would look like if I didn't do t.copy, because t would keep changing and we'd only store the last value. Copy, t gets changed. Oh wow! All right, I just spotted it. It's name mismatch. So I told it to plot the last value of temperature right here in the function. So I just sort of hard coded. Hey, ignore that value I just calculated for you. Yeah. All right. Well, one of those silly bugs. There we go. That looks a lot more reasonable. So it starts out resembling our initial conditions where it's like flat at 50 in the middle, and then it just kind of smoothly takes its shape. And so this kind of reminds me of the graph where we had the parabola appearing when we did relaxation method, but the interpretation here is actually very different. This is not taking the shape numerically. So this isn't just our simulation working on getting the right solution, and the right solution is a straight line. Every single frame of this is the right solution. So this is the time-dependent temperature, and the temperature goes from being basically like a sort of a step function into this nice smooth line with some actual time dependence. And we could plot the value of t here, like on our graph, if we wanted to see at any given snapshot of time, like like right now, whatever right now would happen to no, stop moving. There, whatever right now would happen to be, like this would actually be what the temperature profile looked like. Okay, so we're a little bit different here. Even though there seems to be in the code a lot of similarities with relaxation method, this is not quite the same thing. It's actually a forward Euler method, so that the idea being, as long as h is tiny enough, each of these steps is time accurate.